ideal cycle. When we say ideal means what? Ideal means this is the best already. But best doesn't mean can implement. So sometimes cannot be implemented. So we're going to learn what are the processes that make up the carbon cycle. And we're going to use the TS diagram to describe the cycle. This is very important. So what you learn in chapter 2, just a previous chapter, you're going to apply here. And not only here, you also apply this in Mr. Lim class in the gas turbine cycle. Okay, gas turbine, you're going to learn the Brighton cycle. So again, you will use the TS diagram to describe the cycle. And it's the same as, because gas power cycle is also part of the power cycle. The turbine cycle is part of the gas power cycle. Then, after that, we're going to learn all these auto, diesel, and dual combustion cycles. Okay, we're going to learn the concept, the theory, and calculation. Okay, and what are the assumptions for these air standard cycles? Okay, the processes that make up the auto, diesel, and dual combustion cycles are important because you must memorize, no choice. You must memorize. It's not like given to you in the blank. You have to memorize what is the processes that make up these auto, diesel, dual combustion cycles, and how to draw the PD diagram and TS diagram. Okay, how to draw. Okay, again, how to draw. Need to memorize or not? I would say in a way, yes. But more important is your understanding. Once you understand, you will know how to draw. Then solve the problems. Okay, today I try to target weekend before 10. Target. First time. I try. You do your job, I do my job, still can finish in time. Okay. Yeah, I do know all of you also tired. Okay, let's start with the first one, the Thermo cycle. Okay, this is a French guy. Okay, he lived quite many years ago, more than 200 years ago. So his name is Nicholas Leonard Sadi Carnot. Very long name. So the family name is Carnot. So he's a very good scientist. However, he doesn't live so long. He doesn't live so long. So he passed away about at the age of 36 years old. Okay, so he's a very brilliant scientist in those days. However, he just lived in the wrong era. Which era? He lived in the era of Napoleon. That era, so it's a very chaotic period during the French period. So he come out with this idea called Carnot cycle. Okay, he come out with this idea. And this is the most efficient cycle that you can conceive. He's the first one who write this technical paper. He said that if you want the engine cycle to work well, you must have these two processes where heat supply at constant temperature and heat reject at constant temperature. Okay, you must have these two processes where heat supply at constant temperature. So this is one process. Then heat reject at constant temperature as well. Then in between, so in between these two constant temperature processes, okay, in between these two, these are constant temperature process. Fixed temperature means constant temperature. So it's an isothermal process. So between these two isothermal processes, you have isentropic process. You have isentropic process, which is reversible and diabatic process. So he said a best cycle is made up of these four processes. So isentropic process, isothermal, then isentropic, then isothermal again. So in case you ask how it works, okay, basically it works this way. So to describe this process, we use TS diagram. We use TS diagram to describe the process. So first of all, we have heat supply at constant temperature. Heat supply at constant temperature. So we call isothermal heat supply, constant temperature process. So in previous chapter we say that when you have a process take place, the area under the process line is the heat transfer. So this area is exactly the heat transfer. Okay, so this area is exactly the heat transfer. So this is one process, one process. Then he said after this supply, you have isentropic expansion. So this is where the work output takes place. Expansion. This is where the work output takes place. So isentropic, so it's a vertical line, no change in entropy. S1 equal to S2. S1 equal to S2, the same entropy. So followed by another process called constant temperature heat reject. Constant temperature, so isothermal heat reject. So same thing, when you have a process like this, the area under the process is the heat transfer. In this case, it's the heat reject. So means this area is the heat reject. This area. So finally, you have a final process called isentropic compression. Isentropic compression. So it's a vertical line again, because no change in entropy. So entropy S3 and S4 is the same. So isentropic compression, this is where work input takes place. Work input. So you have heat supply, work output, heat reject, then work input. So this is the ideal Carnot cycle. Ideal Carnot cycle. So based on what we learned earlier in the first law of thermodynamics, when we have a series of processes and finally return to the initial stage, for example, like a car engine cycles like this, when we have a process followed by another process, followed by another process, followed by another process. So it's a continuous process. Then followed by the last process. So there are 4 processes make up this cycle. Then it comes back to the original point. So back to the initial state. So when you have a thermodynamic cycle, this is one cycle. We make up of 1 process, 2 process, 3 process, 4 processes. So these 4 processes make up of this cycle. So when we apply the energy equation, which is the non-flow energy equation, to solve on this cycle, non-flow energy equation, which is from 1 to 2, 2 to 3, 3 to 4, 4 back to 1. So 1 to 2, 2 to 3, 3 to 4, 4 back to 1. And the energy equation is, still remember, is Q minus W equal to delta U. So we have 4 processes, so I call summation. Summation means the sum of all the heat, sum of all the work is equal to the sum of all the heat, internal energy change. So let's do one by one. So one by one means what? Q1 minus Q12 minus W12 equal to U2 minus U1. Q23 minus W23 equal to U3 minus U2. Then the rest, same for the rest. So basically you compute for all the 4 processes. Then what you do? You look at the U. The U, you notice that there's a negative 1 here and a positive U1 here. So these 2 you can cancel because it's negative positive. Then the same for U2. Negative U2, positive U2. Then U3 also. Negative U3, positive U3. Then the same for U4. So basically the right side becomes 0. So what does it mean? Means the sum of heat minus the sum of work equal to the sum of change of internal energy, but now internal energy change is equal to 0. So what this implies? Means the sum of heat is equal to the sum of work. Okay? So meaning to say the net work, this sum of heat, this sum of work here is the net work. This sum of heat is the net heat. So basically means if you want to calculate the net work of a cycle, we are talking about a cycle, where we have a process back to the same point again, come back to the initial point. Then you want to calculate the net work, you can use the net heat. You can use the net heat to calculate. So net heat is the heat supply minus the heat reject. So meaning say if you want to calculate net work, usually we use work output minus the work input. We can also use the heat supply minus the heat reject to calculate. So we can use either one of these, the answer is the same. So with this understanding, let's go back to the Carnot cycle. Okay, because this one I think I covered before. Just that I mentioned once, I said you don't understand, never mind, I will still talk about this again. This is the second time I'm going to talk about this. So because we're going to use this concept in our gas power cycle. So I start this with the Carnot cycle. So just now the Carnot cycle, the TS diagram look like this. So we say net heat equal to net work. Net heat equal to net work. So net work is work output minus the work input, or heat supply minus the heat reject, as what I mentioned earlier. And when we want to calculate the thermal efficiency of the cycle, you just use the net work over the heat supply. So net work is work output minus the work input, or you can use the heat supply minus the heat reject. So that's why I say it's equal to heat supply minus the heat reject. And divided by the heat supply here. So now the question is, can you replace the heat supply and heat reject by the number here, the T1 and S1, S2 and S3, S4? Can be done, huh? So let's look at heat supply. Okay, where is the heat supply? Heat supply is the bigger square, bigger or rectangle. So this area here, bigger rectangle. How to calculate the area of the rectangle? So it's basically the base height. So height is T1. So that's why I say height is T1, so it's T1 here. How about base? Base is the width. So the width is this point minus this point, the length. So what is this point? This point is S1. This point is S4. So it's S1 minus S4. So S1 minus S4. So we have this heat supply here. This is the area. How about the heat reject? Okay, heat reject is the lower rectangle. So same thing, to find the area is base times height. Height is T2 now. How about base? Base is T2, S2 minus S3. So we have S2 minus S3 here. Okay, T2 times S2 minus S3. So heat supply again below, so you have T1, S1 minus S4. Now you look at this one. We said earlier, this is isentropic process, S1 is equal to S2, and here also isentropic process, S3 equal to S4. So basically means S2 minus S3 is the same as S1 minus S4. It's the same as S1 minus S4. So if these two are the same, means this one and this one is the same, so I can cancel, so I left with T1 minus T2 over T1. Since S1 minus S4 is equal to S2 minus S3. So basically I get this. So meaning to say, if you want to calculate the thermal efficiency of Carnot cycle, what you need to know is only these two parameters, which is T2 and T1. T2 and T1. So you can calculate the thermal efficiency of this Carnot cycle. Okay, so it's very easy to calculate, just based on this. Okay, so this is the ideal cycle, the best efficiency you can find, given the pair of temperature. A pair of temperature means you have these two temperatures, one higher, one lower. So if this Carnot cycle is the ideal case, why is not implemented? Okay, why is not implemented? Okay, so I will ask you this question. Can you heat up air? Let's say I have air. I want the air to receive heat, but temperature cannot change. Do you have a way to heat up air but cannot increase temperature or not? But I want heat supply to go into the air. Possible? Almost impossible, I would say. Very practical to do. So how to heat up air at constant temperature? Difficult. If you ask me, I also have no way to do that. Same thing for heat reject. I want the air to reject heat at the other side. but the temperature cannot change. When we say cooling, normally temperature drop, but you want the air to lose heat, but temperature cannot drop because we mentioned earlier isothermal process. So these two alone is already quite difficult to implement for gas power cycle. So it's difficult for the system to receive heat and reject heat at constant temperature. Okay, so in practice it's difficult to have a system to receive and reject heat at constant temperature. Normally, when we say we heat up the gas, when we say we heat, temperature should increase now. Okay, and you normally increase the temperature, and you also may increase the pressure, or you may keep the volume constant. Okay, you may keep the constant volume or constant pressure. Another thing is the Carnot cycle. Carnot cycle has a low work ratio. Carnot cycle has a low work ratio. So what is work ratio? Okay, the definition of work ratio is this. Based on the network that you calculated earlier, network, which is this one. I come back to this again. This is the network. Network, which is the work output minus the work input. Okay, network, or heat supply minus the heat reject. So this is a network. Okay, so the network divided by the gross work. What is gross work? Gross work is the work output itself. Okay, so work ratio, which is the network divided by the gross ratio, divided by the gross work, the ratio is quite low. That's why Carnot cycle is also not implemented. But this is low. This is one thing, but the major concern is this: difficult to heat up gas or reject heat from gas at constant temperature. Quite impractical to implement. Okay, for this reason, Carnot cycle is not employed in a power plant. For example, in gas power cycle. Okay, so this is theoretical cycle, but implement difficult. So you may say, if you ask me why this Carnot, this guy, go and implement or come out technical paper saying a Carnot is an ideal cycle. The reason is he doesn't live long enough. Okay, he only live until age of 36. So if let's say given him time, he will come out something even better. But unfortunately, he didn't live long enough. So someone continue his work and come up something come out invention, but using their name maybe. It's not using this Carnot, this thing. So because of this Carnot cycle is not implemented. So the ideal cycle will be based on this following cycle, which we got the carbon ratio. And in this case, we are talking about the system, the working substance, assumed to be air. So we're going to cover 3 important air standard cycles. Okay, we're going to cover this important one because they are commonly used today. And these are the practical reciprocating engines run in the practical reciprocating engine on the road today. Okay, the first one is the Otto cycle. Some of you may have heard before, Otto cycle. So Otto cycle is used to approximate petrol engine. Petrol. So you pump petrol. So petrol engine run on this cycle. Next, diesel cycle. So diesel, everyone know. You go to petrol kiosk, you pump petrol. There's another pump is for diesel. So this diesel engine cycle is for approximate the low speed diesel cycle. So there's a word called low speed. So what is this low speed referring? Okay, the low speed, as far as I know, talking about the RPM of the engine running speed. So during normal load running, with load running, if the RPM is lower than 600 RPM, it's considered low speed. Normal speed is with load. So then you look at normally when you look at the lorry, taxi, buses, which most of them use diesel engine. they use diesel fuel engine. Question is, are they running on this diesel cycle? If the RPM is lower than 600 RPM. But you look at the lorry, the RPM is easily hit 1000, 2000 RPM. The buses also 1000 plus 2000, even 3000. The taxi is even higher. So some of the diesel taxi, you look at the RPM, 4000 RPM also have. So under load, they are running at 4000 RPM. Are they still considered diesel cycle? No. So these are not for the kind of engine used on the road. Then this is used where? Okay, I'll mention about this later. So those running on the road, diesel engine for buses, taxi, lorry, they are classified under this thing called dual combustion engine cycle. Dual combustion engine cycle. So these are used to approximate high-speed diesel engine cycle. High-speed diesel engine. And high-speed means the engine RPM is more than 600 RPM. Under load, with load, running load, it's not idle speed. Under normal running load, the RPM is more than 600 RPM. Then you can classify this engine under dual combustion engine cycle. Okay, so when we describe this as standard cycles with auto, diesel, dual combustion, we normally use the PV diagram discussed that we learned in your thermal system, plus the TS diagram. So all this, when we draw the time, we base on the following assumption. So there are some assumptions you must understand that we follow. Okay, what are these assumptions? Okay, first of all, these are ideal cycle. These are what we call as standard cycle, very ideal. So when we look at the actual diagram, we call actual indicator diagram. So you'll find that this ideal cycle is different from the actual indicator diagram. Why different? Okay, first of all, the assumption that we are looking at complete thermodynamic cycle. We are looking at complete thermodynamic cycle. And when we say complete thermodynamic cycle means we are assuming the air, the same amount of air in the cylinder, in the reciprocating engine cylinder, this air never go out or come in. So it's under heat expand, then under cooling then it contract. So this air subject to heat but no change in chemical composition. Okay, no change in the chemical composition. No change in the properties. So the working substance is air and is the constant property substance. So what do I mean? We do not consider that there is a change in the chemical properties because we just treat air as an ideal gas and the specific heat capacity are all constant. This is very important because this makes the major difference between what you learn here and what you're going to learn from Mr. Lim class, which is the turbine cycle. Okay, because the turbine cycle in Mr. Lim class, this is the difference because I say this air is an ideal gas and constant specific heat capacity. In the gas turbine, we will consider combustion take place. Okay, what do I mean? Okay, I'll give you a simple example. The air that you breathe consists of 78% nitrogen. How many percent oxygen? 21% oxygen by volume. So this air is a mixture of nitrogen, which is the majority, and oxygen mixed together, plus 1% other gases. During combustion, when the engine takes in the air, you pump petrol, then combustion takes place. What happened to the oxygen? Burn. Become something else. You learn the combustion in your engine tunnel. So you should know already. After combustion, what happened? Become other gases. Become what? H2O become CO2 plus what else? It goes sulfur, then becomes something like sulfur dioxide. Okay? This is what you learn in combustion. So In gas turbine cycle, after combustion takes place, the property of air will change because oxygen disappears. Combine with other gas become a compound. But here in this chapter that we're going to do here, we assume no change because it's a complete thermodynamic cycle. So you just add heat to the air, then the air expands. Then you just add work done to the air, then you compress the air, and then you lose heat. Then you just contract. Something like that. No change in the amount of air. Means you do not let the air come in or you do not let the air go out. It's the same amount of air. Keep on doing the work. Okay, you add heat, expand. Then you lose heat. Then you compress again. Then add heat, you expand. So doing this kind of thing. So it's different from the Stirling one, which is the turbine cycle, where air coming in, combined with the fuel, then combustion. Then because of combustion, the property of air changes. So that's a major difference here. Okay. So also here that all the processes in the cycle are reversible. Okay. All the processes in this what we study here is reversible. Okay. This is also another important thing is because coming to Mr. Lim class, the expansion process is especially or sometimes even the compression process is not reversible. Okay, so to make things even more complicated. Okay, I don't want to confuse you, but let me assume everything is reversible. Okay, everything is constant. The properties are all constant. So the property of the gas is air. And this air having the same property, no matter where is it, the property no change. Okay, so this at least make your calculation a lot easier. Okay, TS diagram. Just a quick recap before let me cover a few more steps and you go for break. Okay, TS diagram very important. We're going to cover PD diagram and TS diagram in this cycle. So that's why I need to do a recap. Recap means refresh your memory. PD diagram, constant volume is a vertical line. So bigger volume is just on the right side. So constant volume line on the TS diagram is this a curve like this. So this is what you learned in chapter 2. Bigger volumes on the right side. So this is constant volume line. How about constant pressure line? Constant pressure is horizontal line. So let's say 1 bar. Let's say this 1 bar. How about the 1 bar on the TS diagram? It looks like this. Okay, 1 bar. So higher pressure, just draw a higher line. Just draw a higher line. So I mentioned before. So what this line represents? Let's say this point. This point. So this point means the pressure is 1 bar. The volume is V1 or maybe 1 meter cube. I don't know. So 1 bar V1. So this point. So this point is corresponding to this point. Same thing, this point, which is P1, B1, B2, correspond to this point, P1, B2. So this point corresponds to this point. So this is how you relate the 2 points. So let's say you have another pressure P2, same thing, I have these 3 points here. So this point, which is P2 and B1, correspond to this point. P2 and P1. So this is how we relate the 2 points. So P3 is the high pressure, so you just draw higher. So if you have a constant volume process, the constant volume process on the TS diagram, is this one, on the PV diagram is vertical. Okay, this is constant volume process. One more time. Constant volume process. Then come back. So this is how we relate the constant volume on the TS diagram and PV diagram. And how about constant pressure? Okay, constant pressure look this way. So I have this constant pressure process from this point 0.1 to 0.3. So from 0.1 to 0.3 this way. Then reverse, come back. So this is how we relate the two diagram, PV diagram and TS diagram. Okay, so let me quickly do this one first, then go for break. Okay, the first one I'm going to talk about is Otto cycle. So it's named after this guy, Nicholas August Otto. So he won roughly the period before this just not the one that Carnot passed away, 1832. So after that he probably pick up some idea from there, then he come up this idea called Otto cycle. Okay, this is the guy. So how this thing works? He said that I will have a process that approximates petrol engine cycle, whereby I have a first process called isentropic compression. Isentropic compression means compress the gas isentropically. So you see this is the isentropic process. Isentropic process. So this is the same as this one, but this is just on the PV diagram, this is on the TS diagram. Then the heat is added to the air. So inside is air. After you compress the air at very high pressure, then I supply heat to the air. Okay, in the actual engine, how the heat supplied to the air is by spark plug ignite the fuel mixture, then cause the combustion take place. But in this ideal cycle, we say that it's the heat added from outside to the cylinder. Okay, the heat added from outside the cylinder. And this thing takes place very fast. So fast so that the piston haven't moved and the combustion or the heat supply already finished. That's why this is a constant volume process. Means heat added to the cylinder but piston haven't moved. That's why it's constant volume. So you have the constant volume process. Constant volume process. So after the heat added to the air inside, pressure becomes very high. Temperature also becomes very high. Then what next? This high pressure air will push the piston down. So this is where the work output takes place. You push the piston down and do work. Behind the piston, you have the connecting rod, you have the crankshaft, and cause the engine to run. Okay, so this will cause the engine to rotate because of this work output. So what kind of expansion it is? Isentropic expansion. Okay, isentropic expansion. So after the air expand to this point, the pressure drop, the temperature also drop. But this temperature is still higher than the original point, still higher. Then what happened? You have this constant temperature heat reject. You have this constant temperature heat reject, constant volume heat reject. Means the volume remains constant. Then you lose heat outside. Lose heat to the outside environment. So it's a constant volume heat reject. So no change in volume here. You can see it's a constant volume line here. So this completes the Otto cycle. So there are 4 processes. Okay, one more time. Isentropic compression. Piston compress the air from here to here. Isentropic compression. So the piston compresses the air from this point to this point. Then you supply the heat to the air inside. Supply heat inside. Pressure increase. Temperature also increase. Then the high pressure air will push the piston down. They push the piston down and do work. Okay, this expansion is isentropic expansion. After the expansion, temperature is still very high at this temperature. Then you have a constant volume heat reject. So the heat reject to the outside, constant volume. So this is the ideal Otto cycle. Ideal Otto cycle. Okay, let me show you this video, then you go for a break. Or you want to go for a break first? Yeah. Where's my cursor?
and is considered to be a technological milestone of human soul. It was named after its inventor, Nicholas August Archibald. Archibalds were used in motorcycles, cars, and other vehicles. This animation explains the Otto engine as a four-stroke engine. This engine is composed of a piston that moves up and down in a cylinder. The highest point the piston can reach is called top dead center. The lowest point it can reach is called bottom dead center. The volume between both points is called engine displacement. The pistons connect to the crankshaft through a connecting rod. The crankshaft transmits the rotational movement to the gearbox and consequently drives the wheels of a car or motorcycle. Two camshafts are installed on top of the cylinder, which control the intake and exhaust valve. The camshaft is connected to the crankshaft through a belt. More often than not, the crankshaft to camshaft gear ratio is 2:1, which means that for every 2 revolutions of the camshaft will rotate only once. An Otto engine has a spark plug that uses an electric spark to ignite the fuel charge. A four-stroke Otto engine is an internal combustion engine in which the piston completes 4 separate strokes. The first stroke is called intake stroke. Here, the intake valve is opened by the rotating cam. The air fuel mixture is sucked into the cylinder. The second stroke is the compression stroke. The intake valve is closed and the air fuel mixture is compressed to a high degree by the piston. The higher the compression ratio, the more mechanical energy the engine can squeeze from the air fuel mixture. Higher compression ratios, however, make self-ignition more likely. The third stroke has been named power stroke because this is the process where power is produced. The air fuel mixture explodes. The force created by the explosion causes the piston to move down. The fourth stroke is called axial stroke. In this stage, gases remaining in the cylinder are removed from the cylinder through an exhaust valve. The crankshaft transmits the rotational movement to the gearbox, and the driver can drive. Often, engines of today feature more than one cylinder to power cars or motorcycles in order to increase speed and smoothness.
Okay, let's go for a break. Come back about 7:50 or 7:55. Okay, this is the basic construction of the engine block of petrol engine. So normally petrol engine, you will see the cylinder head. You see a cylinder head where you have the intake valve and the exhaust valve. Then you also, for petrol engine, you definitely will see this item called spark plug. Here's spark plug here. Then you have this piston where it slides inside the cylinder. So this is a cylinder here. So the piston is connected to the crankshaft through this thing called connecting rod. And the piston movement across the crankshaft to rotate. So this is how the linear motion transfer to become rotational motion. Okay, so this is how you transfer the motion. So basically how it works is when you have air coming in, air coming in, then compress, then combustion or heat supply, then exhaust. Very quick, huh? So what I show you here is the 4-stroke engine cycle. 4-stroke. So 4 stroke, this one, the piston move 4 times. 1, 2, 3, 4 times. So this 4 times, in case you wonder where is the fuel, let's say in the actual engine. In the previous time, the fuel are injected before the intake valve. But today, some engine they have direct fuel injection. So direct fuel injection means the fuel injector is installed right after the suction valve. So because of the latest technology, construction is very different. What's the purpose? Better fuel efficiency. Better efficiency. And this is, if I have time, I will explain a bit on that. And then another time. Okay, so this is the 4 stroke. Okay, 4 stroke. So the suction stroke, where the air coming in, then you have the compression stroke, which is the isentropic compression. Then you have this thing so-called the power stroke. So the power stroke comprises of 2 things. The combustion of the air, or so-called the heat supply inside the air, and cause the isentropic expansion. Then followed by the exhaust. Exhaust means you push out the exhaust gas. So in the ideal gas standard Otto cycle, you only look at this one. So you do not take into consideration about this. So the heat supply of the air we consider is a constant property air. Constant property air, and you do not have combustion, just heat added from the outside cylinder and heat reject from the cylinder to the outside. So it's slight different in this area, slight different. So the piston slide from this position to this position, from what the video mentioned earlier. This position is a name called bottom dead center. Okay, bottom dead center. Then the top position, the highest position is called top dead center. So the piston slide between these 2 positions. So if we ask, can the distance keep changing or not? The answer is no. The position, the piston move from here. The piston move from here to here is always fixed. You will not change during operation. Okay, but the car engine is made. This is how you move. You cannot say, can I move a bit further or can I lower a bit further? No way. Because the car engine, because of the crank mechanism, the way it's designed, once it's fixed, it cannot change. So then this volume that the piston strap through is called the strap volume. Strap volume. And this is, in layman, we call this engine displacement. Okay, so when you buy car, you normally look at car catalog, and they tell you 2000 cc, 3000 cc. This 3000, 2000 refer to this cylinder, this displacement, we call strap volume. Okay, how to calculate this volume? Very easy. It's a cylindrical volume. Pi d square over 4L. Okay, pi d square over 4L, where the d is the diameter, L is the stroke. Okay, so this is the displacement. Then next, you have the top part where we call this clearance volume. This clearance volume. So this is where the piston cannot reach. So this is the clearance volume. So now we have this thing calculation called volume compression ratio. Volume compression ratio. How to calculate? So volume compression ratio, we use this item, this symbol called RV. What is R? R stands for ratio, V stands for volume. So RV is the volume compression ratio, and the concept is the volume before compression is this volume. So you look at the PV diagram is V1. So this is the volume. At point 1 is V1. After you compress, become this volume, and this volume is V2. So this ratio is calculated by V1 divided by V2. So V1 divided by V2. So this is how you calculate. Then you look at this V1 here. This V1 comprises of these 2 volumes, strap volume and clearance volume. So you have these 2 volumes here, strap volume and clearance volume. And V2 is the clearance volume itself. V2 is the clearance volume. So V1 is the strap volume and the clearance volume. V2 is the clearance volume itself. So means you want to calculate the volume compression ratio, use these two volumes add together, then divide by the clearance volume again. Okay. So this is how we calculate the volume compression ratio. So let's look at some catalog then that will give you some relation so you can relate. So let's say this is very common car on Singapore road, very common car. Okay, this is Mazda 6. Then you look at this engine catalog, you see 4-cylinder, DOHC means double overhead crankshaft, 16 bar. Okay, this one not related to our topic here. But more important is the displacement. So the displacement say is 199 cc. It's almost 2000 cc so it's about 2 liter. Okay, then another engine option is 2488. So what are these? These are the shape volume. Okay, so they are 4 cylinders. So 4 cylinder, this divided by 4, almost every cylinder is about 500 cc. Almost every cylinder. Okay, how about the cylinder size? Also given to you, the bore times stroke. Bore means diameter, times stroke, this is the L. Then you see this compression ratio. Compression ratio, this is the volume compression ratio. So this is 14 to 1, this is 13 to 1. Okay? So 14 to 1, 13 to 1. So just now I say some of the fuel injector is inside the cylinder. This is one of them. Fuel system, direct injection. So direct injection means the injection is directly inside the cylinder. Okay, but this is not our topic today. This one concern that has been. Anything else? Okay, so normally when you buy car, I think, or you buy any vehicles, normally what you concern is the car fuel consumption good or not good. So you look at here. Do you want to buy a car the fuel consumption like drink water? You know what's the meaning of drink water? It means you pump, today you pump petrol, 2 days later you need to pump again. Afternoon pump there. Oh, your gas tank leak. Afternoon pump. Normally 2 days later is considered very bad already. Even if you ask the taxi driver, they drive the whole day, I don't think they pump petrol every day. So 2 days is considered quite fast already, but they drive every day. So let's say you're a normal driver and you drive only a certain distance, and you need to pump petrol every 2 days, it's considered quite frequent. It means your fuel consumption very bad. And this fuel consumption here is something related to the efficiency of the engine. If your efficiency of the engine is not very good, but of course this is not only concerned with the efficiency of the engine plus other things like the body weight, the gear ratio, is it efficient, the transmission efficiency, everything in. But one of the key factors is the fuel efficiency. So if the engine efficiency is not good, then of course this one won't be good. Okay, some fancy car let me show you. Fancy car like Maserati, BMW. Okay, Maserati a lot of people like nowadays. Even in the HDB, I can find this car parking. Not my car. Where I wait for the car like this. If I drive this car, I don't need to come here. Okay. V6. So you know what's the meaning of V6? So there are 6 cylinder, 3 cylinder one side on the V shape. Okay, the arrangement is a V shape. So the displacement is 3000 cc, 2979. So almost 3000. So every cylinder also about 500 cc. Okay, the compression ratio, this one is on the low side, it's 9.7 only. But this is double charge car, double charge. So that's why the compression ratio is not very high. Because you have another turbocharger. Turbocharger is the pre-compressed air. This one is 4 cylinder, this is BMW, so it's 2000 cc, so one cylinder about 500 cc again. Then compression ratio 10 to 10.2, slightly higher than this one. Okay, so what you learn in the displacement in the sweat volume, this is the sweat volume. This is the sweat volume. Compression ratio, this is the compression ratio. Okay, so this is the one. So when it comes to calculation, you see this table, scared. Don't scare This one given to you. So you must be familiar with this table, how to apply this table to do your calculation. Okay? This will be given to you. But as I always say things like this. If I give you something and you do not know how to apply, then you only can look at it but don't know how to start. Okay, so you must familiar with the whole thing and know what to use at the right time. Okay, what to use. So let's come back to the Otto cycle, and I start with this isentropic compression. Otto cycle. Okay, just now I say isentropic compression means you compress the air from point 1 to point 2, isentropic compression. So this is where the work input and compress the air. So isentropic compression for the TS cycle is a vertical line. So this is the isentropic process. So isentropic, still remember, is a reversible adiabatic process. So reversible adiabatic, I look at adiabatic, this table. Okay, just look at this table alone, just adiabatic. Okay, now I want to calculate what? Temperature and let's say pressure at point 2. Pressure at point 2. So what should I do? I want to find the pressure at point 2. So what I do is I look at this pressure related to volume. Why volume? Because I can change the volume to volume compression ratio. I can change the volume to volume compression ratio. How do I change? Okay, I just shift my D1 to the right side. I shift my P2 to the left side. So I shift my P2 to the left side. Then the B1 to the right side. Then become like this. Okay? So this V1 divided by V2 is volume compression ratio. So this is how I calculate the P2. So V1 over V2 is the volume compression ratio. So this is find pressure. Next one I want to find the temperature. Find the temperature here. So to find the temperature, what should I do? Okay, I'm going to use the temperature here. Respect to the volume again. I always refer to volume because volume I can change to volume compression ratio. So what I do is, okay, let's write this equation here. So you can see this V1 over V2 is the same as this one, it's a volume compression ratio. So I put it as volume compression ratio, RV. T1 I shift to the right side is multiplied. So this is how I use this to get the temperature at point 2. So this is the first process, isentropic compression. Okay, this is a closed system process, closed system because no air flow in, no air flow out. Throughout the whole cycle, we never talk about the bar open and close. All the bar, consider the bar is never open before. So the same amount of air is still keep on compress, expand. Okay, the same amount of air. Okay, next we have the constant volume heat supply. So how is supplied? Constant volume, no change in volume. So constant volume line. So since we are talking about constant volume, so just now the formula table, I look at the constant volume only. So if you want to find the temperature after the heat supply, what is the temperature here? So I look at here. Temperature and pressure, I only have these two items. So to find T3, I shift my T3 to the left side. So become T3 equal to T2 times P2 over P3 over P2. So this amount of heat supply can be calculated using this, based on the equation provided here. But take note, this is capital Q, capital Q. So MCV T3 minus T2. Capital Q here. So this is the second process, constant volume heat supply. Okay, next, isentropic expansion. Isentropic expansion. So you expand from 0.3 to 0.4 isentropically. Isentropic means no heat transfer, but also no change in entropy, vertical line here. So since this is isentropic again, we look at the reversible adiabatic column. Still the same table, same column again. So if you want to find P4, what do you use? I will come back to this again. I'm still using this. So what do I do with the number? Okay, now the table always show you 1 and 2. But the process I'm working on is 3 and 4. So what you need to do is change the number here. This 1 become 3, this 2 become 4. So change the number here. 1 become 3, 2 become 4. Then shift the 0.4 P4 to the left side. I shift this one here. Basically, is this one go down, this B4 go down, so it become divide. So I just swap the position. So become P3 times B3 to the power gamma divided by B4 to the power gamma. So I just swap the position. But now what is B3 over B4? Okay, I'll talk about this in a moment. What is B3 over B4? So let's do the other one first, which is T4. How to find this T4? Okay, to find this T4, same thing, I will use the same tables. Temperature relate to volume. So same like this case, I need to change the number. 1 become 3, 2 become 4. So I change the number accordingly. So 1 become 3, 2 become 4. So I just shift my T3 to the right side. What I want to find is T4. So shift the T3 to the right side. Now the interesting part is here. You look at this PV diagram. PV diagram. B1 and B4. Is it the same volume? Same or different? Same, huh? So this B4 is the same as B1. So I can put this B4 replaced by B1 here. How about B3? Is it the same volume as B2? Same, huh? So B2 and B3 is the same. So I can change this to B2. So basically what I'm going to do is, this B3, I change the wording to B2. And this B4 and B1 is the same, so I change to B1. So this becomes like this. Then the next thing is, we said earlier, compression ratio is B1 over B2. Right? This is Bs plus Bc over Bs. Now, I have B1 over B2 is RT. How about B2 over B1? So become invert of compression ratio. Invert. So if you cannot catch me, use a simple example. Simple example. Anyone don't understand? 8 divided by 4 is equal to 2. So then I put the other side. 4 divided by 8. Can you see? So same thing. 2 equal to 8 divided by 4. So 4 divided by 8 is 1 over 2. 1 over 2, something like that. So this is how you invert. So do the same here. I'm going to invert this one. So become invert of the compression ratio. So meaning to say, if I want to find T4, I use T3, which I looked up earlier, when times this 1 over compression ratio to the power gamma minus 1. So this is how I do the calculation at point for temperature. Then last process, from 4 back to 1. Last process, from 4 back to 1. So last process, from 4 to 1. This is a constant boiling process. So what you need to do here, temperature at 0.4 empty form. So I can directly use this heat transfer here to find the heat reject at this process, the heat reject. So this heat reject, okay, basically this heat reject can be calculated using this. So MCV T4 minus T1. Okay, I will do the change later. So in this case, this is MCV T4 minus T1. So in summary, the total heat supply is the constant boiling heat supply here. This is the heat supply. So MCV T3 minus T2. And the heat reject is at the constant boiling heat reject here. So it's MCV T4 minus T1. So once you have these two, you want to calculate the work done. Okay, work done, I mentioned earlier, you can use the work output minus the work input. This is the net work. Okay, work output is the expansion from 3 to 4, expansion work. Work input is from 1 to 2, compression work. So when you calculate, you can calculate using these two, work output minus the work input. So if you ask me how to calculate these two, using the formula table, which is this table here, you can use this to calculate. Okay, you can use this table to calculate. Okay, where? Okay, adaptive, calculate work done, you can use this one to calculate. But very tedious, very tedious. So can be done, but tedious. So another way to calculate is, since we know the heat supply and heat reject. So since we know the heat supply and the heat reject, so alternately to calculate the network, we use the net heat, which is the heat supply minus heat reject. So this is another way you calculate and you get the same answer. Doesn't mean you calculate this way, you get different answer. It should be the same answer. Okay, this is provided there is no losses. No losses. Okay, so once you get all this network and heat supply, you can go and calculate the thermal efficiency. Okay, thermal efficiency, how to calculate is the network you calculated earlier divided by the heat supply. Okay, so in case you want to use formula, okay, I don't recommend you to use formula. Use formula means you have to derive something like this. You have to calculate your thermal efficiency this way. Then based on process 1 to 2, T2 is equal to this, then T4 equal to this. Then calculate this way, then put inside the formula. This is the formula. Then you simplify become this. This is the formula. And if you ask me, is this formula given? No. Only this one is given. Only this first one is given. So this one is not given. So if you want to test your memory, if you memorize wrongly, sorry, you write wrong, you answer wrong, I mark you wrong. I can't give you marks if you do wrongly. That's the fact. Okay, so please understand. So the best is still calculate from the first principle, which is network over the heat supply. First principle. So here I also want to show you something. For petrol engine, what affect the thermal efficiency of the petrol engine? Okay, the thermal efficiency, after you simplify until like this, you notice finally there's one factor here, which is compression ratio. The gamma is fixed already, 1.4. This one you can't change because it's F. So the only thing you can change is compression ratio. So you notice that this compression ratio, how it affects the thermal efficiency. So if this compression ratio is very big number, very high. So 1 divided by a big number below to the power something, but it's big, then this becomes a small number. So 1 minus a small number become very big. So meaning say your compression ratio, the higher the better. So that's why today the compression ratio for normal engine is about, let's say just now you saw the Mazda, come to 14 maybe, 14. You recall 20 years ago, those who live long enough, just recall 20 years ago, do you see any car compression ratio 14 one? No turbocharged, 14. Those days, the compression ratio is something like 8 or 9 point something, very good idea. 8 point something, 9 point something, very good idea. Then slowly they increase to 10. So today you can see 14. So my latest understanding is Mazda going to come out a new engine. I can't remember the call. Now it's called F8G. Then they're going to call F8X or Y, I can't remember. So Mazda is going to come out a new engine. The compression ratio as high as 16. Almost like a diesel engine, as high as 16. Haven't come out, but testing, still testing. Maybe launch in the market very soon. Okay, this is the latest engine. 5 years already. Okay, other manufacturers they still prefer to go for turbocharging. So turbocharging is also another form of compress the air before the cylinder compress another time. So it's another form of higher compression ratio. Use turbocharger is to compress the air first, right? Then go into the cylinder. So the air coming into the cylinder already pre-compressed. So the pressure is already high. Then you compress one more time. So that's why the compression ratio is much higher. So other manufacturers they prefer turbocharged engine. But Mazda prefer non-turbocharged, they call normal aspiration engine. But based on the engine to compress the air further. So the higher the compression ratio, the better. So some students may say, oh, if higher better, then might as well you just go all the way to 20, 25, 30. I would say it's the limitation by the control itself. If your compression ratio is too high, what will happen is, let me go back to this. Let me go to, so that you can understand what I'm trying to say. Okay, come to this part, compression. When you compress, higher compression ratio, 0.2 pressure will be very high. 0.2 definitely the pressure is very high. This pressure in pocket here will be very, very high. Okay, so your engine block must be very sturdy, very strong. That's one thing. Secondly, this is the killing part. You compress to a high pressure ratio, the T2 also very high. So this T2 after you compress, temperature also very high because this is high compression ratio. If this is very high, imagine when you compress the time, you compress the air and fuel together. It's a mix of air and fuel. So you compress at this high temperature, let's say 1000 over degrees C. Yes, and the engine oil will start, the fuel will start to explode already before the spark plug. So if the engine fuel start to explode before the spark plug, there's a phenomenon name called knocking. This is why knocking takes place. When knocking takes place, the engine will be, how to say, it will cause damage to the engine, particularly the suction and the diesel pump. Okay, so this is not good. That's why for today, engine, the compression ratio, you can see 14 is very high already. But now, Mazda want to test 15, 16. So let's see, Okay, so we are here. So the engine thermal efficiency.
The thermal efficiency will come up.
This one? Yeah. Okay, very good question. When I come out, a question asks you to derive from this. Do you want me to test you? Oh, okay, good. I will not test you. I only ask you. I never ask the full time like that. Full time, I don't need to ask. I say everything in the textbook will be tested. Yeah, true. Everything in the textbook will be tested. Everything, including this one. Everything in the textbook will be tested. But to you, I ask you, you say no. Yeah. Good night. Huh? Too late already. Okay, let's do one example. Okay, talk, but never do. That's very quiet. Let's do one example. Okay, this is in your textbook. Okay, after doing this example, you can do the textbook. The textbook tutorials. So at least there is one tutorial question on this. At least there is one tutorial question. I'll talk about this later on. So let's talk about textbook examples first. Okay, this question is like this. So the engine operates on the ideal Otto cycle. So very straightforward. They tell you it's an Otto cycle. Very straightforward. Then this cylinder has a bore of 68 mm and the stroke of 80 mm. So they give you the information. Need to use or not? It depends. See what the question asks later. So now the suction condition. Suction is point 1, the very first point. The suction condition, the pressure. Okay, when you see a unit like this, a kilonewton per meter square. What is this? Kilopascal, yes. Kilopascal is what kind of property? Pressure. Okay, some students don't know. So this is pressure. This one you know, you see degree C sure know. Every day you measure temperature before you go to work. Degree C, this is temperature. But again, when it comes to calculation, remember to convert this to Kelvin. Okay, remember to convert to Kelvin. Then next, they say the maximum point temperature is 1350 degrees C. Okay, maximum point temperature 1350. So which point? Later when you draw the TS diagram, we'll see. We'll know which point. Then next, they say the clearance volume is 10% of the straight volume. Clearance volume is 10% of the straight volume. Now sketch the TS and TS PV diagram. PV and TS diagram. Okay, how to sketch? Okay, this one need to sketch. You need to do. For here, for my class, this chapter, I only need you to memorize 3 cycles. Auto, diesel, low combustion. Thursday, I don't know which Thursday start. I think next Thursday. Mr. Lim will start. No, not next week. The week after next. Mr. Lim will start the turbine cycle. And how many cycles you need to memorize? 4. You know, already mentioned.
That's what you mentioned.
No. Mr. Lim one, turbine cycle. Mr. Lim one. At least 3. At least 3. So again, you have to memorize, no choice. Okay, so here, side by side. Side by side, easy to compare. So normally I draw on the left side is the PV diagram. On the left side. Then on the right side is TS diagram. Normally. So how to start? I start from the first process, from this point. I call point 1. This point 1. Where I have an isentropic compression. So I have an isentropic compression. So this is a PV diagram. This is the curve, basically. Sometimes my hand not so steady, so doesn't look very good. So PV diagram. So this is the PV diagram, isentropic compression. On the TS diagram is a vertical line. Just a vertical line. From 1 to 2. 1 to 2. draw over a bit. So after the two isentropic compression, then you have the constant volume is applied. So constant volume, no change in volume, so you draw a vertical line on the PV diagram. Constant volume. On the TS diagram, constant volume line, this is what you just learned in your chapter 2. Constant volume line. Constant volume to 0.3. 0.3 here. So just now was isentropic, so please indicate isentropic. Okay, what I write S equal to C, it means entropy S is equal to C constant. Entropy, S represents entropy is equal to C means constant. So it means no change, just like T equal to C means no change in pressure. So after the constant volume is applied, you have the isentropic expansion. Another curve coming down. So isentropic expansion. Until 0.4. So after that, the last process is the constant volume heat reject. So constant volume is no change in volume, so it's the vertical line again. Constant volume, vertical line again. So on the TS diagram, constant volume line, constant volume line. So what do you need to indicate besides all this information? Pressure and temperature.
Yes.
And what else? Anything else you need to indicate?
Right. Volume.
Okay, normally I would suggest please indicate that the heat supply at the constant volume. Heat supply at the constant volume. You at least must draw this in one of them. It can be constant in the PV diagram or in the TS diagram. Then the heat reject at constant volume process again. Heat reject. At least one of them. If you draw on the TS diagram, then you don't show here, it's okay. But at least you must indicate in one of them. Yeah. Then what next? You indicate that from this point 1 to this point 2 here, this is the sweat volume. Yes, this is the sweat volume. Then this point 2 to the base, this is the clearance volume. Point 2 until the base, this is the vertical line. The vertical axis is the clearance volume. Then what else is you need to indicate that the temperature given to you. The first point pressure 103. So this first point, the pressure is 103 kilopascal. Kilonewton per meter square. This is first point. And the temperature is 28 degrees C. So the temperature here 0.1, 28 degrees C. If you convert to Kelvin, you plus 273, 301 Kelvin. 301.
And the maximum.
The maximum, yes, very good. Maximum is 1350. You look at the TS diagram. Which one is the maximum point? 0.3. Very obvious that they are 0.3. So it's 1350 degrees C. You plus 273 1623 Kelvin. Okay. So now I take out this so that I can write something here. Okay, now they want you to calculate the following thing. First one, compression ratio, which is this. This is the compression ratio. V1 over V2, which is Vs plus Vc over Vs, compression ratio. Next one, calculate the net work. Okay, net work, which is the work output minus the work input. Or you use the heat supply minus the heat reject. So I write in here, to calculate the net work. To calculate the net work per kilogram of the air, you can use the work output minus the work input. Another way is to use the heat supply minus the heat reject. Okay, you use the heat supply minus the heat reject. So now, how to calculate the heat supply? How to calculate the heat reject? So you must know the temperature to calculate the heat supply. Same for the heat reject. You must know the temperature in order to calculate the heat reject. So means you need to find the temperature of all the 4 points. Okay, all the 4 points. Then next, calculate the ratio of maximum pressure to minimum pressure. Okay, maximum to minimum pressure. Max to minimum pressure. So you look at the PD diagram, maximum pressure is this point, 0.3. P3 is the maximum pressure. Minimum pressure, 0.1. So means you must find P3 later on in order to calculate this one. So P max over P minimum, this ratio is based on P3 divided by P1. Based on P3 divided by P1. So then next, the thermal efficiency, D. Thermal efficiency. Okay, definition of thermal efficiency is always based on net work divided by the heat supply. Net work divided by the heat supply. So meaning to say, if you copy the net work from here, you copy the net work here, put it here, you divide by the heat supply, you get a thermal efficiency. So everything all start with this thing, which is the heat supply and heat reject, which you need the temperature. So how to get the temperature of all these 4 points? Let me show you step by step. Okay, so I did this table here, so I show you this table. This is the only thing you have, and you need to know how to make full use of this to get the calculation. This is the only thing you have. Okay, I start from this point called point 1. Not point 1, I start from this process called isentropic compression. But before I do that, let's do the compression ratio first. Compression ratio first. So compression ratio is V1 over V2, which is equal to Vs plus Vc over Vc. Now the question is, do we need to calculate the volume in order to calculate this? Vs plus Vc over Vc. Yeah, Vs plus Vc over Vc.
The other side is BC, is
On the left.
Oh, I write only here. Sorry, my mistake. Vs plus Vc over Vc. My mistake. Okay, Vs plus Vc over Vc. So now you need to calculate the volume or not? Okay, you can calculate the volume to get this. This is one leg. The shortcut way is, what I need is I only need the ratio. What ratio? They say the clearance volume is 10% of the shed volume. So what this thing implies is clearance volume is 10% of the shed volume. So I only need this. To just this alone, I can calculate the compression ratio. So this is how I'm going to do. So BS plus BC, which is 10% of the sweat volume, which is 0.1 BS. So 10% is 0.1 without fraction. Okay, 10% is 0.1. Then divide by 0.1 again of BS. So on top you see BS plus 0.1 BS. This is equal to something like A plus 0.1 A. So you get 1.1 A. Can you see a picture? This is almost like A plus 0.1 A. So you get 1.1 A. So BS plus 0.1 BS, so you get 1.1 BS over 0.1 BS. So once you have this, then the BS and BS can cancel. So you have 1.1 divided by 0.1. So eventually you get 11. So means this engine, the compression, the body compression ratio is 11. Yeah, just like that. That's all. Okay. So after this, let's look at the formula table. So if you are not given the compression ratio, if this is not given to you, please use this to calculate the compression ratio. So some question they give you the compression ratio, then you can skip this. You can skip this part. If this is not given, then you have to calculate. Why you need to calculate? Otherwise, you cannot proceed with the rest. You cannot proceed. So after this is done already, secondly, we need to find all the temperature point. Remember this I mentioned? We need to find the temperature in order to calculate the heat supply and the heat reject. Sorry? Did they give you? They will give you information like the clearance volume is how many percent of the sweat volume.
Okay. That also can be.
Yes. Okay. Compression ratio is not given. They will give you the clearance volume is how many percent of the sweat volume. I don't want. Okay, let's come back. So now we need to find the temperatures. So you see how many points you have? You have 1, 2, 3, 4, 4 points. But point 1, the point 1 temperature is given already. Point 3 also given already. So we need to find the remaining point, which is point 2 and point 4. But you cannot just jump straight to point 2 then point 4. Very difficult to get answer. So I will teach you a systematic step by step. So you always follow this step. Sure you can get the answer. So this is how I would recommend you to do. Okay, starting from this first process. First process is the isentropic compression. Isentropic compression. So first process, I write it here. 1 to 2. Isentropic compression.
I don't know.
So you're doing which one is it?
Huh?
Question B, is it?
I haven't do question B.
Oh, okay.
Let me find all the temperature first, then I will do question B.
Alright.
Because for question B, I need to find heat supply and heat reject. And as I say, this one depends on the temperature.
Okay.
But so far, I only have these two temperatures, 1 and 3. So I need to find 2 and 4.
Alright.
So to do that, we go step by step, find all the temperature first. Then we do the calculation of heat supply, heat reject, and the length. So this is my recommendation, how you do. So start from the first process, the 1 to 2, isentropic compression. So first thing I want to find the temperature at point 2. To find the temperature at point 2, I use isentropic means adiabatic process. So adiabatic is this one. Okay, and to find the temperatures, T2, yeah, I shift a bit, you cannot see the power. So to find the temperature, use T2 over T1 equal to V1 over V2 to the power gamma minus 1. Where this V1 over V2 is RD, compression ratio. So let's do it here. So T2 over T1 equal to V1 over V2 to the power gamma minus 1. V1 over V2 is compression ratio. So RD to the power gamma minus 1. So to find T2, I put T2 on the left side, then shift the T1 to the right side. So I just put in all the number T1 301 compression ratio we just found here 11 gamma 1.4. So this is gamma 1.4. Correct. 1.4 minus 1, 0.4. So what do you have? Okay, this is the temperature. 75.46. Okay, if you convert to degree C, something like
512.
yeah, very hot. 500 degrees. So you imagine that you compress the air together with petrol, having combustion, already very hot. So you compress a bit more, what happens to the petrol? Burn. Haven't stopped, you burn already. So that's why I say it's a problem if you have a high compression ratio. Okay, so now you have P2 already. P2, it's all done. P4. Next, I want to move on to T4, but cannot. You jump this way, you will have problem. You have problem. So I will suggest you to go to the next point, T3 first, from 2 to 3, slowly one by one. So because now happen that T3 is given to you, so a lot easier. But I will suggest you to do T3. So from 2 to 3, this is a constant volume supply. From 2 to 3, constant volume supply. Now temperature at point 2 is already. Temperature at point 3 is already. Let's find the heat supply at this process, which is this one. Constant volume.
MCV.
MCD T2 minus T1, so it's T3 minus T2. Change the number accordingly. But this is capital Q. I'm going to change this to small q per kilogram. So divide by M, so this becomes CB T3 minus T2. We divide by M, Q divide by M, we get small q. So this one divide by M disappears. So Q23, I call Q23 from 2 to 3 equal to CB T3 minus T2. So CB is 0.718. 1623. Okay, 1623, correct. Minus 575.464. 146. What do you have? 601 kilojoule per kilogram of air. Okay, so this is from 2 to 3. Next, I'm going to find the next one, which is 0.4, the temperature. Okay, so I do step by step. So this is the suggestion I have. Don't jump. You jump, sometimes you will. This question you jump, maybe you can understand, but the next question then you have problem. Okay, I still do it here because I still want to use the figure on the right. Okay, after 1 to 2, 2 to 3 will be 3 to 4. Step by step, very systematic. You won't go wrong. So this time round becomes expansion, isentropic expansion. Step by step. So isentropic expansion. I want to find this temperature at point 4. I want to find this temperature. So same thing again. I will use this. Now I change this to T4 over T3 equals to V3 over V4. Isentropic is reversible adiabatic. So I use the same equation, but I change the number. So it's T4 over T3 equal to V3 over V4. Gamma minus 1. So then you come to this PV diagram. Look at this PV diagram. D1 and D4 is the same. Constant volume. Same thing for V3 and V2. V2 is the same as V3. Constant volume again. So means this V3 is the same as V2. V4 is the same as V1.
11.
Okay. So I put this inside. So become compression ratio 1 over compression ratio. Because V2 over V1 is the invert of this V1 over V2. Okay, it's the invert of this. So I want to find T4. So shift my T3 to the right side. So it's T3 times 1 over compression ratio to the power gamma minus 1. So you just put the number inside. T3 already given is 1623, 1623, 1 over compression ratio is 11, 1.4 minus 1 half. So what do you get? 621.9. 621.9 Kelvin. Yeah. So why I take this one? Okay, you know that V3 is same as V2. V4 is same as V1. So I put this inside. So it's V1. I put this inside as V2. This one I have V2 over V1. Okay. So if you don't understand why like that, PV diagram. V1 and V4 same volume. V2 and V3 same volume. Yeah. Yeah, until here, any question? So we are up to this point here, point 4. So the last process, so systematically, just do it step by step, don't jump, then you won't go wrong. The last process is from 4 back to 1. The last process, from 4 back to 1. So this is constant volume process. But this time around is a heat reject. This time around is a heat reject. Okay, I don't need this table now, so I off it so that you can see better. Here now is a heat reject. So what I do now, all the temperature I have already. I have this temperature, I have this temperature. So I can straight away calculate the heat reject. Just calculate the heat reject. So this Q41 is exactly the heat reject. CD. Now we use T4 first, minus T1. Use the higher temperature minus the lower temperature. T4 minus T1. So T4 is 621.9 minus 301. What do you get? 230.4. One more time. 230.4. You. 0 0 0 there. Okay, so you do this systematically everything will be automatically calculated for you, systematically. So you can notice as you do along, your heat supply you calculate already. Your heat reject you calculate already. Okay? So easier for you. But I haven't covered this one, but let me do part by part. Okay, so with this, now we can calculate the network. Okay, network is equal to heat supply minus the heat reject. Where the heat supply is the heat supply at constant volume. This is the heat supply. So it's Q23. So it's 601. 601. Heat reject 230.4. Then you just subtract, you get the answer. This will 6 So this is how systematically you get the answer. Okay? So now you get the put down the network. Next, calculate the maximum pressure to the minimum pressure ratio. And the maximum pressure is P3, 0.3. So how to get this pressure? How you get this pressure? Okay, this is what I was suggesting to do, to find this pressure. Okay, I'll show you the table again. To find this pressure, what I will do is, I will use 1 to 2, find this pressure at point 2, find this pressure at point 2, then use 2 to 3, find the pressure at point 3. Step by step. If you want to do the reverse way, let's say I use 1 to 4 or 4 to 1, find pressure at point 4, then 4 to 3, find the pressure at point 3. Cannot. But then you say you'll find the calculation a bit messy. I will prefer this way from 1 to 2, 2 to 3. Okay, which is straightforward. So from 1 to 2, I want to calculate the pressure at point 2. What can I use to find the pressure? Which is adiabatic process, reversible adiabatic. This is the one to use.
1 to 4.
I'm talking about 1 to 2. Not straight from 1 to 3. Not straight. Because from 1 to 3 there are two processes. So I start from 1 to 2, then 2 to 3. So from 1 to 2, this is the process I'm going to use, which is the adiabatic process. P1, B1N, P1, B1 gamma equal to P2, B2 gamma. My unknown is P2. Now I want to find P2 first. So I shift my B2 to the left side first. I do it this way so that you can see the picture. I shift my B2 to the left side, so become divide. So I have B1 to the power gamma, divide by B2 to the power gamma. Same power. I can combine these two together and put it outside the bracket. Put outside the bracket. Now you see this B1 over B2 is what? Compression ratio. RD. That's why I say P2 is equal to P1 times compression ratio to the power gamma. From here you can put in the number and calculate. So P1, the pressure is 103 kilopascal. So 103. Remember the unit is in kilopascal. Then RP is 11 to the power 1.4. So what they have? One more time? 2956.6 kilonewton per meter square. So now I have P2 already. Next, I want to move on to from P2 to P3. This is a constant volume process. So let me show you the constant volume. Let me shift a bit. Okay, constant volume. Constant volume. equation of state, I want to find, okay, I change the number accordingly. Now I'm looking on 2 to 3. So 2 to 3 means the number I change from 1 to 2, then 2 become 3. So now I want to find this P3. So P2 already found. T2 found. T2 already have from here. How about T3? T3 is given. T3 is given. So now T2, T3, T2, T3 are given. Then we can find a T3 already. So I use this one to find my P3. So this is what I'll do. P2 over P2 equal to P3 over T3. Okay, based on this. Unknown is P3. So if you shift the P3 on the, okay, I shift my T3 and capital 3 to the left side. So become P2 times T3 over T2. Okay, so my P3 is equal to P2. P2 is 2956.6 times T3, 1623. Divided by T2, 2785.46. So what is my P3? 61 one more than 49 point 6149 49 oh sorry 49 kilonewton per meter square. Okay, so we have P3, we have P1 given, so we can calculate the maximum pressure to minimum pressure ratio. So now we can do the part C. So part C, maximum pressure to minimum pressure ratio. This is equal to P3 divided by P1. So P3 is 6109.7. P1 is 103 kilopascal. So what do you have?
$59.
59. So the ratio is 59. Ratio is 59. So after that, last one, thermal efficiency. Thermal efficiency. So thermal efficiency very straightforward the formula. So thermal efficiency always based on the network that you obtain here divided by the heat supply. So the network is 370.6. Heat supply is 601. So what do you get? Six. 616. 0.616. If you want to convert the percentage, just multiply 100%. So 61.6%. So this answer.
Efficiency must be percentage.
I haven't covered the total combustion. I haven't covered the diesel. Never mind. So let's do one question on the tutorial, which is the same as this one. Okay, try this question on your tutorial question, which is question 1. Okay, in case you allow me, I use the slide for a moment. I don't have this question. That's the moment. That's the moment. Okay, on your tutorial, this question, first question, if those who use textbook will be first question. I think in your notes to be the same question. So an engine operates on the ideal air standard Otto cycle has a bore of 10 cm and a stroke of 12 cm. At the beginning of the compression process, the air is 29 degrees C and the pressure is 101 kN per meter square. Quite similar to the example given. Then the maximum temperature in the cycle is 1560 degrees C. Okay, the maximum temperature also given to you. Just now my temperature is 1350. Now this one is 1560. Then the clearance volume, just now said, just that. The clearance volume, it says that it's 12% of the shear volume. It's 12% of the shear volume. Then sketch the PV and TS diagram. Same thing, sketch the same TS diagram, PV diagram. For this cycle, exactly what you're supposed to do is do this one, these two diagrams, PV and TS diagram. Then calculate compression ratio. Same thing, calculate this compression ratio. This first thing you must calculate. If not given, this one must be calculated. Then calculate the network, same as what I just did. Then calculate the thermal efficiency. So you notice, they never ask you to calculate what? The pressure ratio. This one, they never ask you to calculate. So if they never ask, you can skip this part. This part you can skip. This one you can skip. This one you can skip. Because they never ask, so you can skip. If you do the time, you can skip this part. Those bracket is in green. Okay, so you just need to calculate the temperature, calculate this one, calculate the temperature, calculate this one. The green one you can skip. Okay, so it's the same working, same working method. Okay, so you try first. Try this question. Okay, this is the first tutorial assignment for this chapter. This one very important. Wait, one at a time. So it's very important in master the process. This is isotopic because this is constant volume. Isotopic is reversible identity.
So,
It's a big symbol. Look like an N, it's a longer thing. Divided by this one. Stroke length, no. Stroke length is fixed by the engineer. Usually, we must see the calculate the volume. So you must know how to calculate the volume. Yeah, engineering, please. Always, this is also statistics. This is generic always like that. So this is why I say the auto cycle is fixed almost correct. Never change. Yeah. It's always like that. That's why this process is fixed. For auto cycle, it's always the isotropic, then constant volume, then isotropic, constant volume. You never see isotropic, then constant pressure. If that either is another type of cycle, different cycle. Yeah. So this two. Yeah, every time you go. Then you follow this method. Exactly, you'll calculate the work done. By the way, this textbook, it say work done. The work done refer to the network. Sorry, the work done refer to the network. So the work done, to be more correct, to be network. Yes. Okay, do this question, then keep it first. Then next week, we will do the dual combustion cycle, then you submit it together. So at the same time, the previous assignment that you submitted, I mark already, I leave it here. Before you go back, you collect back. Okay? The last question. This is only question 5. How about question 4?
You did not finish your sentence.
diesel. The name diesel doesn't refer to this guy. Doesn't refer to this guy. Diesel. Okay, diesel cycle, I just give you some introduction. I'll cover the detail next Monday, but at least I'll give you some introduction first. Okay, diesel cycle is the heat supply is at constant pressure instead of constant volume. Okay, it's not under this guy. This guy, his name also diesel, but different guy. This guy is the modern guy. Look very handsome. So it's under this guy. And this guy again is a very poor guy. Really poor. You guess, you look at the name, you can guess from where. Okay, so this guy he invented this diesel cycle that the heat is supplied at constant pressure instead of constant volume. So how this thing works is you have the same isentropic compression. Same isentropic compression, but you notice that I purposely draw this very long. Why? Because diesel engine normally compression ratio very high. Diesel engine normally the compression ratio very high. That's why I purposely draw this very long. Okay, so you compress the air until very high pressure and temperature. Then in the rear engine, in the rear diesel engine, you have this fuel injector. You never see spark plug. So the moment you see fuel injector only but no spark plug, confirm it's diesel engine. Confirm it's diesel engine. So then this fuel injector will spray the diesel fuel in the oil mist form into the chamber, and combustion will take place straight away. No need spark plug. So the moment it's sprayed, combustion takes place. But because diesel is not so volatile compared to petrol, not so volatile. What do I mean? Very simple. If you take 2 cups of fuel, one is diesel, one is petrol, and you put your lighter on top, you think which one to catch the fire first? Petrol, because petrol is very volatile. Okay? Petrol is very volatile. So diesel is not so volatile. But doesn't mean diesel is not flammable. Diesel is still flammable, but just that compared to petrol, not as volatile. So means when you spray the fuel inside, the combustion takes place slowly. So you have a constant pressure process. Okay, constant pressure process. So then the fuel cut off at this point. So no more combustion. No more combustion. But the pressure is still very high because it's constant pressure. Temperature also very high. Then you let this hot air inside continue to expand until lower become to the bottom dead center. So continue to expand. So when you come to bottom dead center here, then you have the same constant volume heat reject. Same constant volume heat reject. So calculation wise, there will be some slight change. Some slight change, but the format more or less the same. But some slight change. So instead of constant volume, now I change this to constant pressure. And now this one becomes constant pressure. So just to give you some idea, give you some. Those who want to continue your tutorial by all means, I just show something new.
An internal combustion engine transforms the clean energy fuel to mechanical energy. These engines, which have been serving mankind for over a century, are the most versatile and economical IC engines. To release the chemical energy in diesel effectively, an atomized form of the fuel is made to contact with high temperature and high pressure air. This energy is effectively transferred as mechanical rotational energy. So the operation of a diesel engine is all about producing high temperature and high pressure air continuously. We will see how this is achieved in this video. Piston, connecting rod, crank, and cylinder form a mechanism called a slider crank mechanism. Here, the linear motion of the piston is transformed to a rotary motion at the crank. In an IC engine, this mechanism is properly supported in an engine block. Cylinder head, valves, and fuel injector are fitted above the engine block. When the piston moves downwards, inlet valves open and fresh air from outside is sucked in, or, in other words, the engine breathes. During the return stroke, inlet and exhaust valves are closed, and the air inside the cylinder gets compressed. During the compression stroke, the piston does work on the air, so the temperature and pressure of the air will rise to a level which is higher than the self-ignition value of the diesel. An atomized form of diesel is injected into this compressed air. The fuel gets evaporated and undergoes an uncontrolled spontaneous explosion. As a result, the pressure and temperature rise to high-level value. The high-energy fluid pushes the piston downward. The hot air does work on the piston, and energy in the fluid is converted to the mechanical energy of the piston. This is the only stroke where the piston absorbs power from the fluid. Due to inertia of the system, the piston moves upwards again. This time, the exhaust valves open and the exhaust is rejected. Again, the suction stroke happens. This cycle, which has a total of 4 strokes, is repeated over and over for continuous power production. You may have noticed that a bowl is provided on top of the diesel engine piston. During the compression stroke, this bowl helps produce air that is rapidly swirling. Thus, the injected fuel gets mixed with the air effectively. The mechanical design of IC engines, particularly that of diesel engines, is a challenging and interesting task. Since the combustion process in diesel engines is never uniform and smooth, they are prone to more vibration and noise compared to petrol engines. Thus, diesel engines require a rugged structural design. Out of the 4 strokes, it is only during the power stroke that a tremendous amount of force is exerted on the piston. So a single-cylinder engine will always have high force non-uniformity as shown. Similarly, the output power will also have a fluctuating nature. But with more number of cylinders, one can overcome these problems. Consider this 4-cylinder engine. Here, 4 different strokes can occur at a time. So the power stroke is always present in the engine. As a result, a 4-cylinder engine will have better force and power uniformity. In short, the more cylinders an engine has, the smoother it will operate. A 4-cylinder engine generally operates on the following firing order. A heavy flywheel, which acts like a power reservoir, further helps in smoothing out non-uniformity of power. A huge unbalanced force arises in the form of dynamic unbalance due to the excessive mass at the connecting rod side. This is negated by providing counterweight on the crank side. Opening and closing of valves are accurately controlled by a pair of camshafts. Camshafts derive motion from the engine. It is clear that the camshafts need to rotate at half the speed of crankshaft. We hope you had a nice introduction on the working of diesel engines. Thank you.
Okay. Those finish the tutorial, you can move. Those who want to stay back and continue, finish the question one, please do. Yeah, at least I think I know.